Hi everybody, thank you very much for coming. Today we have the pleasure to have Jessica Prendi, who is giving a talk about how to discover new physics. She is finishing her master right now, so expect a very, not very technical, but very good talk. Please give her a warm welcome.
Thanks a lot, Matthias. Okay, so my name is Jess. I hope you're all doing well, and thank you so much for coming. And this screen is, okay, thank you. Okay, so today's talk will be on how do we discover new physics. And in general, I would say this is a very hard question to answer within 30 minutes, or 45 minutes more so. But I'm going to be talking about the aspects, what does discovering new physics mean from a physics point, the math, the statistical models behind it a little bit, and then also the more novel approaches on how we discover new physics. And yeah, so let's get started. Okay, this is the content, I already just said that. But yeah, I'll be talking about what is new physics, discovering new physics, and anomaly detection, which is also used to discover new physics. And it's very interesting in my opinion, and also what my master thesis work is focused on, so of course I will talk about this. So okay, let's get right into it. So many of you have heard of the standard model of particle physics. Even if you don't study physics, I feel like most people have heard about this. But what this model does, in the end of the day, is just describe the way all of these elementary particles interact with each other on an elementary level. And what I mean with subatomic is, okay, all of you know what a proton or a neutron is. So the proton, for example, consists of this up thing called there and the down thing, and same with the neutron. And yeah, the way standard model also describes how stuff interacts within a proton, within a neutron. Maybe you also know of the electron. So these are the typical things in the standard model describes. And I would say the theory is super successful. It's very nice. And you know, with all the measurements and experiments made, it has been proven over and over again that this is a very stable, not stable, but like a very good model that works very well in many cases. But still, we have done other experiments that have shown that there are stuff that the standard model just cannot describe. One of these things are neutrinos. So neutrinos are these three particles down here. If we go from the standard model predictions, these are supposed to not have any mass at all, to be massless. But then we discovered that there are so-called neutrino oscillations. You don't need to know what it is. But we have seen because of this that, okay, from the way that if neutrino oscillations exist, which they do, they cannot be massless, or just one of them can be massless. So it shows that, okay, maybe there's more behind this theory. We need to add something to it to explain, for example, that the fact that neutrinos have mass, one of the things. Also, something that the standard model cannot describe is dark matter or dark energy. It's not described in the standard model. And there's also this thing called matter-antimatter asymmetry that's going on. What does this mean? It means we have much more matter than antimatter in our universe the way it is. We do not know why. We just know that it's probably the reason why we are allowed to exist, so to speak. And for example, antimatter, so matter would be, for example, an electron. Antimatter would be a positron. A positron is just a positively charged electron, but all the properties remain the same. So yeah, why do we have this asymmetry? It's also a very big question. And of course, we know that gravity exists. And the standard model doesn't account for gravity at all. And it would be nice to have a thing that could combine all of these together. Okay, so when we talk about new physics, it's always about any phenomena or theory that could extend this theory that we already have, and even, I would say, answer one of these questions that I mentioned above, because, sorry, I keep pressing this button, because, yeah, we know that these things are all a thing that need to be explained, but we cannot explain it yet. Okay, now experimentally, how do we look for new physics? Maybe you've heard of CERN. So there's this huge particle accelerator, this huge ring. It's called the Large Hadron Collider because it really is large. And what happens there is really you have proton. Okay, you can also have other things, but we'll just talk about protons. Protons that are really accelerated at super, super high speed, so almost up to the speed of light. And once they have reached the desired velocity, you let them crash into each other. And through the crash, new interactions potentially might form. And this is what you can then potentially measure as new physics. But okay, and you usually let these protons crash at one of these 4 points, so at CMS, LHCb, ATLAS, ALICE. These are just the different experiments that are at CERN, and each of them have like a huge detector that measures these. So for example, the CMS group is like very present at ETH, and thanks to them I got to see this in real life. And yes, I was super happy about this, and it's super cool to see this huge detector in real life, and I would advise anybody who has the chance to also do this, because yeah, you can see I was cheesing, and it's also how I felt on the inside. But yeah, now a bit going away a little bit from particle physics, now into the math a little bit. So what I'm going to follow is a very basic statistics, so nothing high level, that will in a way give you the idea behind what it takes to discover new physics. So yeah, we'll start off with the probability density function. So I wrote down the definition because the math students like the definition. No, I'm kidding. When you have a function mapping from R to R, it's called a PDF if the following properties are fulfilled, namely if you integrate over the whole thing, the area under it must be 1. Also, every value of it must be greater than 0, and you need to be able to integrate this function. And we can then further define the probability measure with this. What does this mean? It means that the probability of, if you randomly draw a data point from this distribution, for it to land between the interval A and B, you have to do the interval from there to there. So super simple, but I will explain it also with the example. So the most important and used PDF that you need to know is normal distribution, because it's everywhere, and yeah. And what characterizes this function is really the mu, which gives you the mean of this function, and then also sigma, which gives you basically how broad this function is. And this function is super powerful because many measurement uncertainties, we describe them with the Gaussian. What does this mean? I will try to do an Okay, with an example. Can you see if I write here? Yes, okay. Let's say you want to measure something that's 2 millimeters. Should I put it more up, or is this fine? Okay, 2 millimeters big. And you will need a ruler or whatever measuring device that you have to measure this. Now, okay, maybe I'll put it up. So the thing is, if it's 2 millimeters, okay, this is true fact, it's 2 millimeters big. But if you were to, let's say, measure a million things that are 2 millimeters big, you will not always measure exactly 2 millimeters. So if you were to draw the count of what else you measure, so most of the time you will actually measure 2 millimeters. But due to the measuring uncertainty that you get from whatever measuring device you're using, you might be measuring, so this would be 2 millimeters. You might actually be measuring 2.001, 2.002, whatever. And this is the way this will behave. And also on the other way around, so you might measure it sometimes 1.99999, and you might laugh and say, okay, but this is basically 2. Well, it's sometimes these tiny differences matter, and the way this behaves is like this Gaussian. So I hope it makes sense when I say measurement uncertainties sometimes behave like a Gaussian. Okay, good. Now the next point I want to talk about is hypothesis testing, and I personally like to have examples from the real world to actually understand what's going on in the more abstract world. So I'm going to use COVID as an example. Okay, so you have the scenario, you're a doctor, and you have a patient in front of you, and you have reasons to believe that this patient might have COVID. You have to set up your hypothesis that you're testing for. And you set up, we just call this the null hypothesis, H0, patient doesn't have COVID. Then you have to also set up your alternative hypothesis called H1, the patient does have COVID, and you now need to determine whether this person actually has COVID, and in a way you want to then either accept H0 or reject H0. Now, what does this mean, reject H0? That doesn't mean that H0 is 100% wrong, it just means that the probability of H0 being true is just very, very low, and it might indicate for another probability to be correct. Now, when we try to figure out whether a patient has COVID or not, you can have 4 different scenarios in the end: the true positive, true negative, false positive. False positive would be you do a test on a patient that has COVID, and the test comes back as, yes, this person has COVID. This is, I mean, you're not happy about the person having COVID, but this is favorable because you want people who have COVID to the test to agree with you. Same with the true negative. When a patient doesn't have COVID, you want a negative test result. But then you have these two types of errors, namely false negative and false positive. Namely, false positive would be that the patient doesn't have COVID, but you have a positive test result, which is not super favorable, because then you have to do social isolation, and we know it's not that nice. But then there's false negative. The patient has COVID, but we receive a negative test result. This is also not nice because you maybe do not want to spread the illness even further. So you need to find a way to determine whether the patient has COVID or not, while minimizing these types of errors, because you do not want to have these errors present, right? Okay, so we're not doctors, we're physicists, mathematicians, and we're looking now for a test that can actually determine whether a patient has COVID or not. And from the life experience that we had, we know that PCR results can be a good indicator. And in this case, when we let our patient do a PCR test, we get our data point X in R. It's just one-dimensional in this way. And we now have to find the threshold that will let you know, okay, this patient has COVID, this patient doesn't have COVID. What does this mean? I will show it graphically. Okay, so here I plotted a Gaussian. It's probably not medically accurate, but this is just to show you the example. So where does this curve come from? Let's just say you have 1 million patients that do not have COVID. You do a PCR test with them, and this is the distribution that you get. So many patients will have a value within here when they don't have COVID. Some will have some here, some will have a value here. But this is the way that the distribution looks like. This is not medically accurate, please. This is just me with the example, okay? Now, you want to know how would this look like when people do have COVID. You do a test on, I don't know how, preferably a large number of patients that do have COVID, and you measure what PCR result that they get. And this is the population. So most people would have a value like this, some have it like here, some have it like here, but really the majority is here. And now you need to find a threshold W that will say, okay, if the PCR value is above here, we just say the patient has COVID. If it's here, we say the patient doesn't have COVID, based on the PCR results. And the way you set this threshold is by a predefined alpha. And this is all about how much error you want to introduce, like how much of error you want to have here. Because what this area then basically says that if a person has a PCR result above here, you will say they have COVID. But there's always the small probability that this patient actually does not have COVID. And you want this to be like maybe 5%. So you set this alpha. It's predefined based on the domain you're working in. You set this to some value, in our case probably 5% or something, and you say, okay, if you test 100 healthy people, 5 of them will have a positive COVID result, for example. But yeah, you have to set this alpha. But okay, now you know that you will say 5 people have COVID, even if they don't, but this will help us for identifying the people that do have COVID. And here as well, you will have the error here of not identifying the people properly that do have COVID by saying they don't have it. But you still will get so many more people. Now, the goal in the end, in any use of test, so this is a test, I will call it, the result of the PCR, is to find a way to have these two populations, but actually have them as separate as possible, because otherwise you have more of these types of errors. Okay? Yes, okay, now we have our test statistic and we have our threshold set, and now we want to determine the p-value, which just means you take the measurement of your patient and you see where on the spectrum it lands, and then you determine the p-value, which is just an integral over the H0 hypothesis from x to infinity. And if this p-value is smaller than your given alpha that is defined here, you will reject the H0 hypothesis. And what this means is not that H0 is 100% wrong, as you've seen here. It will just mean that the probability of measuring another data point as extreme or worse than the one we just measured is just very unlikely. So yeah, you see it's very important to get this separation. And in our case, I would say we have a good test here. Okay, yeah, you have some errors here, but they're, I would say, small. But what would you do if you have a population that overlaps? So maybe the values of PCR are quite overlapping, and then you don't really find don't have a good power to determine this. Then you would need to look for a new way of testing, or like including more dimensions and then finding a new way to map the population in a way. And yeah, the choice of test, we also can call this test statistics. This is just a term that we use. Now, what would this look like in particle physics? So we have the scenario, we know that there has to be new physics, and we do an experiment, and we want to analyze the measured data. So we have the H0 hypothesis. What we measured is no new physics, it's just background, or what we measured is new physics, and we call the signal. This is just the lingo that we use. And you also have, again, your 4 cases where you have a true positive and true negative. The true positive would be what we measured is actually new physics, and our data analysis agrees on it, and you will win a Nobel Prize, maybe. Then the true negative is what we measured, and it's not new physics, and our analysis agrees that it's not, and this is, I would say, the usual case. But then you have 2 problems, namely the false positive and false negative. Now, the false positive is very bad, I would say, because when you measure something that's not new physics, but you claim to everybody, to the media, to the whole world, oh, we just found new physics, it's pretty embarrassing, as my professor put it. So you really want to avoid this case. But if you have a false negative, this is also not super favorable, because then what you measure is actually physics, new physics, but your analysis says it's not, and you might miss a Nobel Prize. So again, you have this problem that you really want to minimize these errors. In our case, I would say the false positive has a bigger weight, but yeah. So how do we do this? We measure the collisions at the LHC. And you know, each collision, so in the end you collide 2 proton beams and particles, yeah, the physics behind it, I'm sorry, erupt from it, so to speak, and you measure these events. You measure what happens, and each measurement entry is like super high dimensional, I would say even up to hundreds dimensions, and you take like millions of data points. So you really have a lot of data and very high dimensional. And here it's super hard to just pick one dimension like we did with the COVID case. Because with the COVID case, we were like, oh, let's just take PCR and then we have a nice test. But here it's super hard because you cannot just, 100 dimensions is a bit hard to map out, I would say. So what you need is a very well understanding of also where to look within these 100 dimensions and millions of data points. What also is an issue is knowing what the populations of H1 or H0 looks like. And for that, you usually use Monte Carlo data set. Oh, sorry. For that, you use Monte Carlo data sets, which means you just simulate the data of what you would expect. Okay, now back to the COVID case, but now with the high energy physics process. What does H0 and H1 mean here? So H0 is just what we measured is not new physics. And this is stuff that we say this is created through a standard model process. And once again, we refer to this as background. So everything that we know already, so when we see a collision, some event, we can say, okay, this can be described by this and this process of the standard model. But if we have H1, it means we have a collision, some event, and we're like, we're actually not too sure if this is the standard model. It's probably something new physics. It could be new physics. And we refer to this as signal, and it could be anything. It could really be anything. We have no clue. I mean, we do have some clues, but really have no clue on how this could look like, what it could be. So it makes it a super hard search. And because we don't really know much about the signal, we need to have a super precise theoretical predictions on the background. And yeah, this is, I would say, one of the harder aspects of it. Now, how do we do? It's the same as in the COVID case. We need to find the test statistics, but we cannot just include every part of our measurements because some part of the measurements, they're not super, like you don't really gain much information from it compared to other parts of the measurement. So whatever you're looking for, you need to think, okay, so this requires physics knowledge. You think, okay, if I look at this process and this end state, what part would be the most interesting? So maybe an example. When we were looking for the Higgs, the main process, I hope I get this right, we were looking for was that going from the Higgs, we get 2 gammas in the end. So this is 2 photons. Okay, and then, but the problem is that having 2 photons, okay, now going back, when you measure stuff, you never measure the Higgs particle itself. You do not measure this, but you measure the end states because this will decay into these parts. And because you only know this, it could be anything because these as end states, it could come from this super simple process, which is electron-positron annihilation. This also has 2 outgoing gammas. But this back then would be new physics, but this was not. So you need to find a way to be able to differentiate these, and there were a way to differentiate this, but what I'm trying to say is that you would now look at maybe the mass or the energy or the angles of these boys here. You wouldn't maybe look at electrons or anything else. You would look at these things specifically, because if you look also into other dimensions like the electrons or things called jets, they will not give you any information on this process, for example. I mean, it would, but okay, let's not talk about this to some degree. But yeah, there are always some dimensions that are not super useful, and so it really requires your knowledge from both sides. Okay, and then once you have your test statistic, you will event by event determine whether what you have is signal, so new physics, or background, and then you will get some count. This is how much background I have, this is how much signal I have. And from your prior physics knowledge, you know which areas of the phase space, I will call it, are most critical. So you usually look in areas where you expect to have super high counts of S and lower counts of B. And then we once again go back to our test statistics, but here it's a bit more complicated because you have a discrete distribution. You ask yourself how many background events would we expect here, given that we have thinking that we have no signal at all. And then you compare this to how much signal we actually have. And then based from that, you can determine the p-value that you get. And if you get a p-value that's below 2.9 times 10 to the power of -7, then you consider to have made a new physics discovery. This is super hard to achieve, I would say, nowadays. But yeah, it has this strict criteria. I mean, it's really a convention, so to speak. We don't have a physics reason behind this, other than when we do measure something, we want to very, very make sure that this is actually signal and not just the physics that we already know, which is why this is super small. Okay, now enough about the statistics side, and more a bit about the research going on right now. So what do we know about new physics nowadays? So since the discovery of the Higgs particle, so the measurement of the Higgs particle, so to speak, we have not found new physics, at least not at CERN. And you see all of these bulks, these all represent different searches that were made to try to find new physics. And they, from the statistics point of view, just have been unsuccessful at ruling out the standard model. And this leads to think maybe we should change the way we're looking for new physics. And yeah, in general, we know that the new physics process has to be super rare because otherwise we probably would have found it, or have a super high energy, super high mass. So we would need even more data. And we also know that the new physics signal will not be too different from what we already know. And I like to compare searching for new physics, like trying to find a needle in a huge haystack, but the haystack is the needle is super small and might look like the hay itself. So super hard. And the way we try to do the new approach is to, so what we did earlier is we really picked from this huge haystack, we picked one area to look at. Because if you just look at the whole haystack, it's going to be super hard to find it, right? But if you look at one where you think, okay, this could be a good guess where it'd be, the probability of you finding it could be larger, but as we have seen, it was super hard till now to find anything. And now what we want to do is just look at the whole haystack itself, which in some aspect loses sensitivity because you cannot really look through everything as well anymore. But you're trying to consider everything, because if you were to look through every part of the haystack, part by part, it will take ages. And we're now trying, like research is now trying to get through this part where you can look at all of it together. And this is where anomaly detection comes into play. And this would be, anomaly detection, I would describe it as a new way to look for signal without any bias on where the signal could be. So really just looking everywhere. And the way anomaly detection algorithms work is they're designed to detect statistical outliers. And there are many different approaches to this, but I will explain to you one that's machine learning based because hot topic, and the one that's used at CMS at CERN right now because I think it's a very cool approach, the the way that they thought of this. So the architecture that they use for anomaly detection is called autoencoder. What does this model do? So basically you give it an input, and the input has d dimensions, so it's huge. And then the first part of the autoencoder, called the encoder, will compress the dimensions to very small, and this will then be called latent representation. Now from here, the autoencoder, the decoder, has to map this back to the d dimensions. And now you're thinking, okay, but this algorithm just compresses stuff and just reconstructs stuff. What's the use of this? There is use, but it's a very nice thing, because let's just say you train your autoencoder really well to know to reconstruct the standard model process. So you feed it in, this is what standard model looks like, you need to be able to encode and decode this. And when the hope is that when you do measure standard model processes, that in the end you will also get the standard model process back. So you can kind of map an error between these two inputs and outputs, and you can see what is the error, the reconstruction error. Now what would happen if you theoretically would get beyond the standard model input? If you would, let's just assume this was a new physics input, and you would run it through your autoencoder, you would get a much bigger error in the reconstruction. So it would have a hard time mapping input to output with a small error. And then you can use this reconstruction error as your test statistics, as I mentioned earlier, to maybe rule out some stuff that could be signal, could be interesting, and some stuff that could be background. So yeah. Now, as I said, you train the autoencoder on background only, meaning you just feed it how does standard model process look like. And yeah, if you have a low reconstruction error, probably background. If you have a high reconstruction error, probably something anomalous, something weird, probably signal. But then there always remains the questions of, are the anomalous events detected by the autoencoder always potential signal events? Most likely no. And it's also something that a lot of research goes into for this specific question alone. But yeah, for now, we don't have a clear answer. Now, before I end my talk, I want to, if you're interested in the topic, there are 2 lectures, master course lectures, but maybe you can try it in the bachelor, I don't know. Phenomenology of particle physics 1 and 2. Then there are statistical methods and analysis techniques in experimental physics, which really just teaches you how to do data analysis with high energy physics. Then there's this book, Statistical Data Analysis by Glenn Cohen. He also worked at CERN, so it's very high on the particle physics use. And then if you're interested in a semester project or master thesis, you should contact Mauro, who, if you're interested more in the data analysis aspect, you should contact him. If you're more interested in this anomaly detection thing that I've been talking about, you should contact Thea. And yeah, that was it. Before I end, though, I would like to make some advertisement for the coffee lecture coming up on Thursday. It's going to be by Professor Ilaria Azzardo. She's a professor from the University of Basel. She's great. I really advise coming, you, and we will have free pizza and snacks. It's going to be on Hengeberg, and she will talk about the topic of family in academia, because she's a mother and a professor, and I would like to know more about, it's nice to hear about her ways and how she does it, I think. So yeah, would be nice to see you guys there too. Okay, that was the end of my topic. Thank you.